Entry, descent, and landing is about the controlled flight of a vehicle system through all appreciable atmospheres, including safe landing. You've got a vehicle system that's in interplanetary space, approaching a planetary body like Mars. It starts to feel the effects of the gravity. Gravity starts accelerating the vehicle and tugging on it a little bit and changing the trajectory in very predictable ways. Your vehicle system starts to interact with the atmosphere of this planetary body. At first, it's not much. It's just sort of individual molecules hitting against the spacecraft, but as the gravity continues pulling on it and continues accelerating your vehicle, you're getting up to relative velocities of 13,000 miles per hour, and your vehicle system gets pulled in, you're slamming through the atmosphere and creating plasma around it, shedding of wake vortexes, and all kinds of very interesting aerodynamic things are happening, but the vehicle system has been designed to account for these things. You're passing through what would be the peak heating phase, where you're really hitting the atmosphere hard, and then shortly after that you go through what's called peak deceleration, where this vehicle body hitting the atmosphere is helping slow you down relative to the planet through hypersonic velocities and slowing down into the supersonic phase. Once you get into that supersonic phase, you're going to transition to a supersonic decelerator. That supersonic decelerator now has to get you down to subsonic speeds. Once you get subsonic, you then move to your terminal descent system. And so this is what is going to get you completely to the surface and do any potential diverts that are needed at the very end to get you to a safe landing site and touch you down safely. Langley has this very critical role of making sure that EDL will happen successfully, and it's still considered the riskiest part of the missions. There are literally thousands of things that have to go right, and each one of those stages, there are many pyro events that have to go on to make things happen at the right times. The work we do looks at that entire vehicle system. It's over a long period of time and many decades that we've been building up this expertise. We go back to the 1950s hypersonics program. Langley was leading that. Langley had to become good at all the different speed regimes. We led the aerodynamics work for the Mercury program, and we've been a significant part of every successful atmospheric entry, descent, and landing system since then, both at Earth and Mars and other planets. We take the time to develop the tools and the techniques to understand these complex vehicle systems. And we not only develop those tools here, but we use them in mission operation senses as well as in predictive, what would certain vehicle systems do. We have the research facilities, like our wind tunnels here, to go in and underpin these computational tools, and we can take the vehicle system to a hard-to-predict condition and test and understand how it'll behave. Failures have certainly happened. The saying kind of goes, if you're not failing occasionally, then you're really not pushing the edge of what you can do. You're being too conservative. With Mars Polar Lander, there were a lot of lessons learned, particularly on the entry, descent, and landing. We found roughly 7 different ways that that mission could have failed. NASA has set a horizon goal for the agency of getting humans to the surface of Mars. It is a huge technology gap, but at Langley we've been working on this for years, knowing that this is an eventual goal. With today's technology, which is based on the work done here at Langley, we're an order of magnitude away from where we need to be. Over the last 10 years, we've been working on a technology called HIADS, which is hypersonic inflatable aerodynamic decelerators. And these are aeroshell systems that are inflated exoatmospherically, and it has an inflatable structure, and over that it has a thermal protection system, so that as it's coming through the atmosphere, it protects that structure from the heat pulse. The studies that are going on now across the agency, we have the HIAD technology as our point of departure architecture for how to get humans to the surface of Mars. That's why it's important for us to have been working on these technologies for years, because now they are close enough to mission infusion for certain missions that you can see a path to these human class missions. If your system is flying in, through, escaping from, or characterizing an atmosphere, Langley has the knowledge, skills, and expertise to make that system successful.